Okay. So your problems the review problems from last semester are due on Friday. I think I still have to get a couple people Scantron, so if I do, send me an email and I will print those out and send them to you. I sent out some emails last week about some issues with there were two number 104s. So disregard the first one and use the second one that's in a question form as opposed to a product. And then for one of the problems where you're ranking things, there is an F, but there's no F on the Scantron, so just write in the F in the appropriate answer. And for the last reaction, there could be two major products on. Since I didn't tell you to bubble both, just give me one of the major products. Unless I explicitly said double bubble, both answers. There are some questions that may have more than one answer. And it was either designed that way or it depends on your interpretation of things. And that's fine. I'll accept the multiple answers. I've already coded that in, and if not, then you can just bring it to me and we'll take a look at it. And you can tell me how you viewed it. And that's okay, because if people are like, well, I looked at it this way, well, I looked at it this way, okay, my job's done. And hopefully then it helped you review for what we're going to do. So that's due on Friday. And I'll talk a little bit about the in-class quiz that we'll start with on Friday, but it'll be over the reactions for today, of which we'll talk about. Okay. I think that was it. What questions do you have? About the reactions for today, which was mostly Grignards and reductions. So I'm going to ask you questions on Friday. They're going to look like on the sheet that I just handed out, Roman numeral number 2. So those reactions can be, now there's a couple. Well, the good ones aren't even on here. So all the reactions that were in the video and in the handout can be boiled down to a couple reactions, just generically in terms of their mechanism. So first of all, each one of these reactions involves having a C- or an H-. So the C- comes from basically forming what's called a carbanion. Now the problem with carbanions is if a C- and H- are the two strongest bases that we can have. And so the issue becomes, how do you make a C-? This was the initial problem that people had. How do you deprotonate a CH bond if C- is the strongest base that you can have? Because a C- isn't going to deprotonate another C- if they're the same stability. There's no energy there. There's no energy gain. So the way that you have to make a C- is by using a Grignard or an organolithium reagent. And so what people found out was that if you take your carbon and you put a halogen on it, and then you treat it with something like, we'll start with lithium metal, that you get a new type of reaction that we're not going to get into the mechanisms of. They happen all the time. They're kind of annoying because they can go many different ways. They're not free radical, but yet they're not a carbanion-carbocation reaction. They're basically called single electron transfer. So what happens is that I take my lithium metal, which has one unpaired electron. And lithium would love to lose that unpaired electron because then it'll have a noble gas configuration at lithium plus. But what I'm going to do is I'm going to treat the carbon-bromine bond as if it was 2 electrons, which it is. So what I can do is I can think about the lithium then transferring an electron to the carbon, but then I need 2 lithiums so that each one of the lithiums transfers 1 electron to carbon, 1 electron to bromine, and I break that bond. And so when I do that, what I end up forming is a carbon with 2 unpaired with a pair of electrons, a Br with 2 unpaired electrons to go with its 6 lone pairs. So I end up with a C minus and a Br minus. The counter ions to those are the lithium pluses that formed after the lithium lost its electron. So forming these organolithium or Grignard reagents with a C minus is a single electron transfer reaction. It doesn't fit any of our classes. And I'm just showing it to you because this is actually how these reactions work, although there's some question. There's a lot of questions about how these things react, but that's the basics. So when I want to do this with a magnesium, so basically the stoichiometry then is it's going to be 2 lithiums and 1 alkyl halide. Now, I'm never going to balance the equation out. You'll always see organolithium, or you'll always see alkyl halide plus lithium makes the organolithium, and I rarely balance the equation. Okay, so if you're looking at it going, that's not a balanced equation, the next thing, oh, he doesn't balance those equations. I just don't. So don't get freaked out by the fact that they're not balanced. That level of detail is something I'm not worried about. But that's how it works. With the magnesium, however, I only need 1 magnesium because magnesium then has 2 electrons that it can donate. What happens is if I split the CBr bond, I'm going to still make my C with the lone pair, and then my magnesium is still going to be bonded to the bromine, which is still going to be Br minus, but now the magnesium is 2 plus, so the net result is this whole ion is a +1. So when I write a Grignard, and this is truly what is called a Grignard reaction, it's always going to be C minus MgBr plus, because the MgBr plus is net a +1. And so that's like lithium being a +1 as well. And so these reagents are interchangeable in this class. In general, they may react differently on occasion, but that's beyond what we want to talk about. I also did a lot of my thesis and postdoc work was on organolithiums. So if I'm not careful, I could tell you many more details than you want to know. But these are compounds that are used all the time. Okay, so I'm going to make a C minus with a counter ion, MgBr plus or lithium plus. And so this is how I make them, and this is how Grignard made them. He won the Nobel Prize for it. He's in every organic. He will be in every organic book forever. There is nobody who did organolithium chemistry that gets credit for it. And actually, Grignard kind of took what Barbier did with a sodium in order to change it, which it worked better with magnesium than sodium, which is why everybody knows Grignard, but nobody knows Barbier, except people that did research in this like me. And even then, it's questionable. You never see pictures of them. One time I saw a picture of Wirtz. I didn't even know who Wirtz. I know who Wirtz is, but I've never seen a picture of him. So there's a lot of this. Grignard is known the most. So what we're going to say is I want to make a C-. I need to put my bromine on the carbon, which I can do by free radical halogenation. I'm just going to take a simple one. I'm going to add magnesium to it, and I'm going to make a CH3- MgBr+, and we're going to ignore the MgBr+ and just work with the CH3-. Okay, so that's the basis for making a C-. A C- is a strong base and a strong nucleophile. We're going to use it as a nucleophile, but if you looked at, I think in the video or in the book, certainly, if you're doing these kinds of reactions, if they touch water, if they touch air, they're going to deprotonate water in the air. They're going to deprotonate water even that's left on glassware, and so they will die. They will just form CH bonds, and they're no longer nucleophiles. So all these compounds are air sensitive. Some are pyrophoric. They'll just spontaneously catch on fire. That happens. So we always have to work away from water, away from CO2. So if we made something like methyl magnesium bromide, what can I do with it? I can add it to a carbonyl. Now, if you want an H-, our choices are sodium borohydride or lithium aluminum hydride. And so borohydride has 4 hydrogens attached to boron. The boron's delta positive, the hydrogen is delta negative. This is a situation where boron is more electronegative or less electronegative than hydrogen, so it's an H-. So the borohydride has 4 equivalents of H-. Okay. So the stoichiometry there is that if I'm just reacting this with one carbonyl, I only need 1/4 of a mole of borohydride, but each borohydride can give up to 4, and that's going to be important because throughout the semester, if I need all 4, I'll have all 4 available. Lithium aluminum hydride is the same way. The aluminum is attached to 4 hydrogens. The aluminum is less electronegative than hydrogen, so you get an H- and an aluminum plus. So all of these two are sources of H-. H-, strong nucleophile, as well as, again, being a strong base. So with these are also will react with moisture. They'll react with air. Lithium aluminum hydride is much more reactive than sodium borohydride. I always tell the story of my first master's student a long time ago in a building not so far away, but it's a parking lot now. He was working in industry at the time, so he was well seasoned, and just came. In those days, the labs were behind our offices. Like, you walked, the door literally to the lab was in the office. So I came back and he's like, "Oh, the lithium aluminum caught on fire." He was using it to reduce something, and I'm like, "Okay, you don't seem freaked out by that." And I just threw some sand on it and took care of it. Okay. It will sometimes catch on fire if you're not careful. And you don't add water to these because then you would turn the H- into H2. And H2 is extremely flammable, so you throw water on it and it just makes the fire bigger. So the appropriate solution is throw sand on it. So probably other students would be broken down in tears. That didn't happen the next time somebody had a piece of something and it like caught the plastic dish that we were weighing it out into on fire. That was like, is plastic dish supposed to catch on fire? I'm like, did it? Oh yeah, but it went right out. Okay. So all these reagents are what are, they all react violently with water, so we have to keep them away from water. And there's worse reagents than this. So the idea here is I got an H minus and a C minus. How do I generate those? Either I use an H minus reagent like lithium sodium borohydride, or I make it using the Grignard reaction. So this is step one. Make C minus. So wherever there's a bromine, that's going to turn that carbon into a C minus. Next, what we do is we then react that C minus or H minus, and they're going to be exactly the same, with a carbonyl. So in order to remember what happens there, we need to go back to last week, because what happened last week when we took a alkynyl anion and we reacted it with a ketone or an aldehyde. We had an alkynyl anion, strong base, strong nucleophile. What did it do here? So it attacks the carbonyl because it's a strong nucleophile. It needs an electrophile. And in this case, the electrophilic carbon is the carbonyl, which is delta plus. So last week, the C minus came in and attacked that carbon. And if we just had it attack that carbon to form a carbon-carbon bond, I got 5 bonds to the carbon. So what happened at the same time? The pair of electrons moved up to the oxygen, which is perfectly fine because the oxygen is more electronegative. It can handle the negative charge. Why did they put that reaction into alkynyl anions? Number one, it's an alkynyl anion reaction. Number two, it was foreshadowing all the Grignard reactions. So I show you this because I have now formed a carbon-carbon bond. I guess I just have an R group here. So we now formed a carbon-carbon bond with an O minus. And we'll talk about what happens to the O minus in a minute or two. But then that reaction is now over. The molecule hangs out and waits for an H plus to be protonated. And then when it's protonated, we now end up forming the alcohol. And in this case, I formed a carbon-carbon single bond from the carbon-carbon triple bond alkynyl anion. And I may have said in the video, the reason why every organic student has to learn Grignard reactions is because there are certain things that are premium in organic chemistry. First, forming any kind of carbon-carbon bond is a premium reaction. In general, before probably 1900, before 1920, if you came up with a reaction to form a carbon-carbon bond, you won the Nobel Prize, and organic students will know your name forever. It's true of Grignard, it's true of Diels and Alder that we'll talk about later on, but that is the case. So anytime you can form a carbon-carbon bond, where's my little red dot at? Anytime you can form this carbon-carbon bond, that's important. So what am I doing in a Grignard reaction? I'm doing the same thing. As a matter of fact, I could go through and I could erase the triple bond and just put any C minus I want in there. So do the same thing. What if I have a CH3 minus with an MgBr plus? And I react it with, and now here's where the variations occur, and there's only 2 variations. I'm going to react this with a carbonyl, so it's going to attack the carbonyl. What can I attach to the carbonyl? Well, here are my choices. My first choice is either 2 R groups or an R and an H, or I suppose two H's. So I can have aldehydes and ketones, and two H's is formaldehyde, the one carbon aldehyde. So ketones, aldehydes, and formaldehyde all do the same thing. It's all the same mechanism. It's just it might give you a slightly different alcohol. But the mechanism's the same. The C minus comes in, attacks the carbonyl. The pair of electrons goes up there. My R or my H is attached to both sides of the carbonyl. I form an O minus. And then I've added now my CH3. Or CH2 minus, or whatever the C minus is. I've now added it. Okay, so there's a lot of variation there, but it's basically all the same mechanism. All I'm doing is forming that carbon-carbon bond. Now, here's where the reaction can be different. So whenever you do this reaction, I form a CO minus bond. Last week I may have mentioned that carbonyl bonds are very strong. So in general, and I'm giving molecules human characteristics here again, if these molecules are strong, then what happens is, or if the C double bond O is very stable, this molecule is going to say, you know what, I want to remake that carbonyl. That's what I want to do. So how's it going to do that? It's going to try and bring this pair of electrons back down to form the carbonyl. That's what that molecule is going to try and do. Problem is, it can do that if something leaves. Our problem with this molecule is, will you lose a C minus or an H minus as a leaving group? And the answer is no. Why not? Leaving group ability is based on one thing: basicity inversely. C minus and H minus are our strongest bases. Are they leaving? No. Will they ever leave? No. They will never leave. So this molecule's stuck. Its instinct is to reform the carbonyl, but in order to do that, something has to leave. If these are carbon groups or if they're hydrogen groups, that's not happening. So the molecule's stuck. So it hangs out, and what's it do? It waits for the H plus to come in, and this reaction is a two-step reaction. So first I add my C minus, and then when the reaction's over, I add my H plus. That's why in this reaction you will see then H plus. In my problems, you will see something like the Grignard or the carbonyl step 1 and then step 2 H plus H2O. If the H plus H2O was added when the Grignard was present, the H plus would protonate to C minus, and C minus ain't a nucleophile anymore because it's been protonated. So you kill your Grignard. I guess, violent terminology. It's no longer a nucleophile. So we got to keep it away from acid. So we wait until the end to add the acid, and then what do we end up with? We end up with our alcohol. Is it primary, secondary, or tertiary alcohol? It's going to depend on the carbonyl I started with. Did I start with a ketone or aldehyde, or did I start with formaldehyde? So in the book, the idea here is we can start thinking backwards, which we'll do here in a minute. But they'll say, oh, if you want to make a primary alcohol, use formaldehyde, 2 H's attached to the carbonyl. You want to make a secondary alcohol, use an aldehyde and a Grignard. You want to form a tertiary alcohol, use a ketone and a Grignard. But honestly, it's the same reaction. It's the same mechanism. Will you see this mechanism on the exam? Yes, it will be the easiest mechanism you answer all semester. because it's just 2 steps. Okay. So we can think about how to prepare alcohols, but the reality is, if this is a ketone aldehyde or formaldehyde, I'm adding my R group, my Grignard R group, and then it's over. I form an OH. So that's reaction 1A. Reaction 1B is erase all the CH3 minuses and make them an H minus. And then what happened? I reduced my aldehyde or my ketone. So if I wanted to write the mechanism for this reaction with an H minus, and where did H minus come from? Lithium aluminum hydride or sodium borohydride. I would say, okay, I'm going to take, I'll give you a specific example here. We'll just make this aldehyde. I'm going to react this aldehyde with sodium borohydride. Then H plus H2O. I ask you, what's the product of this reaction, which I could ask you on Thursday. I could say, write the product of this reaction. What is sodium borohydride? It is a source of H minus. What's that H minus going to do? Come in and attack the carbonyl. What am I going to make? An O minus. The alkoxide says, I want to reform the carbonyl. It reconsiders since there's no leaving group. All right, I can't do that. I'll wait to be protonated. Then the H plus H2O is added, and I now make, in this case, a primary alcohol. So I reduce the aldehyde down to a primary alcohol. Reduction, this is the organic definition of reduction. Adding hydrogens is reduction. So same mechanism, whether it's R minus or H minus. So if you're adding to an aldehyde, ketone, or formaldehyde, it's a 2-step reaction. Okay. So all the reactions that were in the book, in the video, they all can be, or half of them can be summarized this way. All right, everybody kind of okay with that? We bored? So then what's reaction 2? Reaction 2 is, let me change the molecule slightly so that I use a carboxylic acid chloride, or I use an ester. And I either react those with a Grignard or an H minus. So this is a different kind. This is carbonyl. These carbonyls are going to react differently. Okay, and why would they do that? Because I've altered the structure. And let's start with an acid chloride here. So I take my CH3. I take my acid chloride, I'm going to go ahead and add CH3 minus MgBr plus to that. I'm going to add my Grignard to that carbonyl, to that acid chloride. First step in the mechanism, CH3 minus is going to attack the carbonyl carbon. No different as before. I'm going to end up with a CO minus, and then my CH3, I form my carbon-carbon bond. First step's the same. Now the molecule says, hey, I'd like to reform my carbonyl. All I have to do that is to bring down this pair of electrons. But now what happens? I got a leaving group. I've got a good leaving group like a chloride. So as that pair of electrons comes down, the chloride can leave. That couldn't happen before because that was a carbon or a hydrogen. So the molecule was stuck. Now it's not stuck anymore. So what do? I reform my carbonyl. And so this was the alkyl group that was added from the Grignard. And I would get a Cl minus. So when there's a potential leaving group, and it doesn't even have to be a good leaving group. So the OR group of an ester could leave as well. This will kick it off and it'll reform the carbonyl. Now here's the problem. The problem is that I want to add one molar equivalent of Grignard and acid chloride. The problem is the rates of these reactions are probably slightly different. So remember, there's millions of molecules of Grignard and millions of molecules of carbonyl. So when a Grignard attacks a carbonyl and forms the ketone, if there's any more Grignard around that hasn't reacted, the Grignard can now come in and add to the carbonyl, so that now what I end up doing is now I end up forming the alkoxide, but now the second equivalent of Grignard has added to that ketone in this case. Molecule again says, hey, can I reform the carbonyl? And this time, no, because there's no leaving group. So then what happens to it? It waits around to be protonated so that I end up forming a tertiary alcohol. And in this case, two of the alkyl groups attached to the tertiary alcohol came from that initial Grignard. So if it was two methyl groups or two ethyl groups or whatever the Grignard was, those two groups are going to be the same.
How do you know if there's excess Grignard?
The thing is I have a choice. I can either try and do this reaction 1-to-1. And if I did it 1-to-1, some of that ketone is going to be converted to alcohol. So at the end of the reaction, even if I do this 1-to-1, I'm going to end up with some tertiary alcohol, some ketone, and some unreacted acid chloride because it didn't get a chance to react. Because the Grignard it was supposed to reacted with the thing. So if I want a mixture of these three products, just use 1 molar equivalent. Well, I don't. So what am I going to do? I'm going to say, you know what? Let's use 2 equivalents or excess. Tommy?
You don't react it with like H plus at the end. You just like keep it as tertiary butoxide and then do like some E2.
Yes, but there's going to be all the other stuff in it as well. This is not, if you're thinking that would be a really good way of making tertiary butoxide, I'll give you this. This would be a really good way of making tertiary butanol. Then in order to make tertiary butoxide out of that, we'll need to know those reactions, which I believe are, were they last time? Or they're coming up? They might be coming up. Although I know how to make them. And you do too. So this is a way to synthesize tertiary butyl alcohol. It's actually a way to synthesize any alcohol you want where 2 of the groups are the same. But I'm basically either going to use 2 equivalents of Grignard or I'm going to use excess. So that's the difference in these two molecules. Esters and acid chlorides, I have to react 2 equivalents of the Grignard, and I'm going to basically get a tertiary alcohol of each one of them. One alkyl group came from the original molecule, and the other 2 groups came from the Grignard. So if you're looking for a cue as to what the products are, this reaction will always have to have 2 equivalents of Grignard. Always. So these are the 2 reactions. Of course, what did I do up here? I said, well, let's change the C minus to H minus. Okay? What I did this morning was I actually just copied all this, pasted it on the next slide, erased the CH3, and just wrote in H's. I can't do that in this mode. But that's what we do. Same exact mechanism, only now H minus. And you might say, well, okay, do I need excess H minus? Sodium borohydride has the equivalent of 4 H minuses with it. So does lithium. So in that case, if I used half an equivalent, that would still give me 2 H minuses per carbonyl. So really, in terms of mechanism, there's 2 big mechanisms here, and that's it. So does that kind of make sense? Either one or both of these could be a mechanism that I ask you to do on the first exam. If I'm smart, we'll have a graded homework assignment, probably either Friday or so, given out on Friday or so, and have you do this for practice.
OR leaves the same as the CL, right?
Yes. Now, you may say, but OR minus is a stronger base, so it's, in theory, a worse leaving group, which is true. But I didn't say that it had to be a good leaving group. I was very careful when I said it doesn't have to be a good leaving group, it has to be a potential leaving group. And H minus and C minus are not ever leaving groups. Therefore, they are not potential leaving groups. So OR minus could leave. And so if you wrote the mechanism with the OR the same way, it would be correct now. Later on, I'll modify it slightly so that it makes more sense. So those are our 2 reactions. Reduction with H minus and Grignard with R minus. You can either do it on an aldehyde or ketone, which is add, protonate. Do it with an acid chloride or an ester, add, eliminate, add again, protonate. Does that kind of make sense? So then the question is, well, let's do it. Let's try one. But before we try one of the ones in number 2, which you can do, and I already have the answer key for this written, so I have to push the button and release it. Let's spend a few minutes thinking about backwards thinking, the reverse thinking, which is Roman numeral number 3, problems in Roman numeral number 3. So let's say and I'm going to modify, this is sort of like number 20, sort of like number 20, but I've taken a carbon off of it. Let's say you wanted to make that alcohol. So I have to sit down and I have to think about how am I going to make that alcohol using a Grignard. So what kind of strategy can I think about? Well, here would be the first kind of strategy that I would think about would be this. This CO single bond came from what kind of functional group? What did it start out to be? It started out being a carbonyl. So over here I'm going to have a CO double bond, and so that CO double bond is going to become my CO single bond. Now the carbonyl has two alkyl groups attached to it. And what am I adding to that carbonyl? I'm going to add a Grignard, right? I'm going to add a C minus with an MgBr. So I've got three alkyl groups that I need to worry about. One's going to come from the Grignard, and the other two were already attached to the carbonyl to begin with. So I can say, okay, which two do you want to attach to the carbonyl? Two CH3s, that's a good starting point. So what does a Grignard have to be? CH2 minus CH3. And then of course there would be an MgBr plus. The counter ion to the minus, or a lithium plus, but that's the Grignard I would use.
Can you do an ester or acid chloride? Two atoms are the same and have that.
I could think about that too. I could say, you know what, this molecule has two methyl groups. So maybe I could start with CH3, CH2, C double bond O, Cl, and add two equivalents of Grignard and do the reaction that we just did, adding two methyl groups. So yes, that's another approach. So that would be a second way to make this molecule. And what would the third one be? Because it's just all about combinations. So what would the third method that I would use to make this be? How about same thing? Let's start with the carbonyl. What two groups do you want to attach to it? Or what group do you want to add?
Well, you could attach CH3 and CH2, CH3, and add CH2.
And that would also make. Now all three of these would have a then H plus H2O step, or then H plus step. Now, unfortunately, this is thinking kind of backwards, right? This is thinking reverse. Thinking about, well, how do I make this product? And it's going to take a while to get comfortable with that. You may never get comfortable with that. right? But this is what we have to do if we're going to sit. If somebody says, "Hey, I want you to make this molecule," the first thing you got to do is you got to figure out what series of steps would I use to make that molecule. And so this is just the Grignard step. Where did the ketone or the acid chloride, where did the ketones or the acid chloride come from? What if I can't buy them? Well, I got to make them. Right? We don't know how to make ketones yet. We will. Because what we've been doing is making the reactions for today were new reactions to make alcohols. The reactions from last week were these ones on the first page that were review on how to make the alcohols from previous reactions. Only in this case, what I've done is I've given you answers to choose from. So if you want to use these as practice problems, you can do that. Only on the exam, you're not going to get reagents to choose from. You're going to have to make those up on your own. And I don't mean literally make them up. Because this is not diving, there is no creativity points. So we have to begin to think about, well, how would I make these alcohols from there? Now there's one last reaction. It's a product of that reaction. All right, we're stuck. So how should we handle that? Give up and move on? Possible strategy, but not when it's the last problem. There's nothing to move on to. So, all right, so let me just write enough mechanism to give me the product. So what should I do with my CH3 minus? What have we been doing all day?
Put it on the carbon double bond to acid.
Have it attack the carbonyl. That's what we've been doing all day. How come I'm not doing that? Because that's not what's going to happen. So this is the proverbial trick question. There are no trick questions. There are questions that are meant to ensnare you in a trap. But this may be one of them. But what functional group is this? This is a carboxylic acid. What am I reacting with the carboxylic acid? A Grignard that is a strong base, in addition to being a nucleophile. So what is that strong base going to do? It's going to deprotonate the carboxylic acid. So this is the one time that you do not add the Grignard to the carbonyl. The C- will come over and it will grab the H+, so that I have now killed my Grignard because I have now formed a CH bond, and I have now deprotonated the carboxylic acid to make a carboxylate salt. Right? If you're having deja vu, where have I seen those before lab last semester? Right? Doesn't take much to deprotonate a carboxylic acid. And you're going to see this again this semester because we're going to use bicarb to deprotonate it, sodium bicarbonate. So this is the one reaction where you do not add CH3 minus to the carbonyl. Instead, it deprotonates. As a matter of fact, Grignards, you've got to keep them away from any hydrogen that can be deprotonated. The examples from the video would be water, alcohols, or anything with an NH, and also then a carboxylic acid. So anything with a removable hydrogen, the Grignards have to be kept from, because they will just simply deprotonate it. All right, so that's the one reaction that doesn't fit any of these models, is this one. Because it's not a Grignard reaction, it is a carboxylic, it's a carboxylic acid, it's an acid-base reaction. Okay, so I will send you an email probably early this evening outlining the reactions that you will get. You'll just get a couple of them, or a few of them, at the beginning of class on Friday. Will look like Roman numeral 2. So I'll say here, write the products of those reactions, and that will be the quiz. The purpose of the beginning of class quizzes is simply to force you to kind of review these reactions, because they're going to come fast and furious. Okay. If you have any questions, throw them up on Piazza or come see me. Otherwise, we'll start with a quiz, and we will have the review problems due on Friday as well.